So last class, if you remember, we were talking about the means transverse wave on a string we defined in a particular way, and we saw that what exactly was the conclusion. We said that any function you take of the form say x minus ct, in fact I shouldn't even say that this, I can say that any function you take, it will travel with a speed of c, which is under root of t over rho, where t is the tension that is there on the string and rho is the mass per unit length. So at this speed, this shape will travel. So this is a right traveling wave, and if you write x plus ct, it will be a left traveling wave. And these random functions, arbitrary functions, so they could be anything, and independent, irrespective of what function you choose, the speed will remain the same, and without changing the shape or size, the wave will move. Okay, so that's the thing which we had discussed, and then we didn't even use any differential equation or anything. We just used normal logic of dynamics, and we saw that how and why such a thing is possible. Okay, under obviously these are the proper condition that tension is uniform, density is uniform, everything. So under that condition, this is possible. Now what we will do is we will derive the wave equation, which is generally called as wave equation for a transverse wave propagating on a string. We will derive it. Now how can you derive this? Even from this, okay, even from this argument which we used last class, we can derive the wave equation. How would you do that? What exactly do you mean by this? See, if there is a string on which this wave is passing, so if you take a snapshot, then you will see such a shape, and after a certain time, if you, the drawing I have drawn, I should have drawn it like here maybe. Yeah. So after a certain time, if you draw it, it may so happen that you will see that the like that, right? And this is the distance peak to peak. If I see in time t with c speed, it has moved, right? So this is the way of you can say that you are this picture is like at a given time seeing the shape. But there is another point of view that somebody can stay at a particular location, okay, and then keep on measuring the displacement. The displacement is fixed, and he's measuring the variation with respect to time, right? Now how these two persons explanation about the wave, they will be related. One person is standing at a point and seeing whatever is happening at that location is plotting. So he will get a curve with respect to time, right? So this person is A. So it's A's viewpoint. So he will plot something, whatever displacement he is seeing. Now another guy is he's having a camera, so he's just taking snaps, and he is having a picture of the curve, which is with respect to x. Obviously this guy B, he is having a sophisticated equipment, a camera. This person just having a distance measuring equipment, distance versus time, stopwatch and scale. So now, but these two curves, are they going to be the same, or what is your viewpoint?
They will be partial derivatives of the original f of x plus or minus et with respect to x or t at a particular x value or t value.
Okay, so that means, how will they be related? So the thing, yeah, exactly what you said is, they will be related with respect to their partial derivatives, right? That means, you see this, what you can get from this is, if you change one unit in time, suppose the function changes by delta f, okay, by changing one unit in time, and what happens if you change one unit in space? So that will be, suppose this I call one unit change in time, and delta f s or x, I'll say x is changing by one unit in x space. So obviously, this will be minus c times this, right? So the change in the function which happens for single change, see now, now and for this it is just c into fx, right? Delta ft and delta fx, yeah. So they are related by c times fx, and then what exactly they are nothing but, one is the partial of f with respect to t, right, by keeping the x constant, and you are seeing how the t is changing, that is person A's view, and that is related to say minus c times, and this is changing in x, right? So it is like partial of f with respect to x, right? So that is how the partials are related, and what is the meaning, physical meaning? How do you visualize such an equation? To me, it looks something like this. See, this is what? F is a curve, isn't it? Now, df by dt, or partial of f with respect to time, is that at the same location, what is the velocity, right? This is for A, he is seeing just what is the velocity of that particular point. Now this is the slope at that particular location, right? Now what this tells is that if the slope is negative at some location of f, okay, suppose df dou f over dou x is negative, then this whole thing will become positive. That means the velocity is upwards. That means if you have a shape, then in those portions where the slope is negative, like in these zones, those points will be moving upwards. That's the meaning of this equation. And exactly the same opposite is wherever it is positive, the slope, they are coming down. And that is how the wave actually moves, right? This part moves up, this part moves down, and then keeps on happening. Exactly the opposite thing happens here. That's why it is coming in this way. Now, so if you take just one more time the derivative, so both the sides, you will come to the same thing, right? Again 1 minus c will be multiplied. Here again c will be multiplied, so c square times df by dx, and that's what is written, you know, to club both the things. You can just say that c square right. So this is what is called as the wave equation for the transverse vibration of a string. Okay, so transverse wave equation, and and then clearly it's from this kind of argument, if you derive this equation, it's very obvious that it is the speed of the wave. The c is nothing but the speed of the wave, and f could be any shape that you can think of. Okay. Now this is one way to come to this, but the most usual way that also we should know, because we are now discussing how the wave equation is coming, and once we go to the acoustic wave equation, it will be exactly form wise exactly same, only the parameters will change. So that's why if we understand this equation completely, the acoustic wave equation will be very easy to correlate. Okay. Still once we go there, students sometimes face difficulty in correlating velocities, acceleration and displacements once we go to acoustic, even though this is done at this detail. Okay, so please concentrate on this. Yeah. So, and then to derive in the usual way, you know that thing, right? Means if you take a small segment of the string, so the tension here will be, you know, say suppose it's t, and this is a theta, and say this is also t, and this is theta. So you just basically if this is the vertical, so the horizontal forces, they balance each other, the t cos theta, for small values of theta. So this is very important. In fact, we use the same argument when we derive the other part, that nowhere the distances are so big or the radius of curvature are very small. Those things are not happening. So they are reasonably smooth functions and low height of deflection. So that is the constraint, and that constraint comes here as small theta, for which we can say that tan theta is equal to sin theta is equal to theta, sort of approximation we can use, and cos theta becomes 1. So then if we write, you know, so this t sin theta component, which will be equal to the tan theta component, so we can write simply that if this function is f, so f prime at, say, so suppose this one is at distance x, this one is distance x plus dx. Okay, so this is a x plus dx minus t f dash at x, right? So this is what is the upward force that is acting on the mass, which is equal to rho times dx. But this is nothing but, you know, that means sorry, not the partial f over dx square times dx, right? Because the t you take out, so it is the difference between the slopes. So over a small distance dx, so this is the second derivative. Here I just wrote the mass, I missed out the acceleration. I had to put the acceleration here, right? So this is the force, should be equal to mass times the acceleration. Right? So that's how you get again the same equation, that so del square f by del t square is t over rho. Now this t over rho times second partial of f with respect to x. Now in this derivation, nowhere up till now we say anything about movement. Nowhere we said this. We are just writing an equation of equilibrium, right? And in fact, up to this point also, here we just say that this T can always be positive. It's a string, it cannot have compressive forces, and rho is also a positive quantity. So if it is anyway always be positive, then why not replace with something called c square? So whenever in differential equation we always do that. When something ought to be positive, we can replace that with c square or whatever square to say that it is always a positive number. So now when we write like this, this equation exactly becomes this, but there the concept of speed of a wave is not very apparent, right? So that is why you should always see both forms of, all the forms of derivation, each one having their own strengths and weaknesses. Okay, this is very clear easy to understand derivation wise, but it loses the concept of the speed immediately. Now from where the speed kind of thing will come into picture once you try to solve this equation. Up till this point, nowhere it is mentioned that it's the speed, but once you go to solve, you will say that if I try with function, any function which is of the form say x minus ct, then this is whatever I take for f, if I substitute it here, it satisfies. From there, then you say that okay, this c and this c are the same. So then you say that, oh okay, that means this form now will move with time, with the same speed c. So that's what. So in the previous way, we started with the speed of a wave and came to the wave equation, and this we derived the wave equation, and from the solution we got the concept of speed of that particular wave. Again, this is independent of the shape, because for any function f it will work, and similarly if you put x plus ct also it will work. So again you say that both are the solution. So the general solution will be summation of both. Okay. So that's I think should be fine. Whatever I wanted to talk about the wave equation as such. Anything else I wanted to say, or you want to ask? Yep. Fine then. So that's about the wave equation derivation in two forms. Good. I'll stop here.